It's really weird for us to think that this is how the universe works. You can read about it in a textbook, but it's really weird to think that a particle can be in two places at once. The fact that we can confirm that and that our work shows that is really quite amazing, that we can show that that's how the universe works. This weird quantum weirdness is actually reality.
It's very hard to wrap your head around what's actually happening. So people sort of allude themselves to science fiction and saying, oh, it can't be true, it can't be real.
We know from our everyday observations of the world that's not how the world works in our everyday experience. And that's why it's really important for labs like us to show that yes, at the extremely small scale, it indeed does seem to be how the universe works.
Experimentally, it's extremely hard to sort of demonstrate this. Several people, to our knowledge, have tried in the past to sort of show these effects in the actual experiment, and they have always come short.
So we're deep in the depths of the Research School of Physics at the Australian National University, and we're just heading to our lab, which is a couple of levels underground, so we can build it on bedrock because we have a lot of laser beams and we want the laser beams to be nice and stable. It doesn't really look like very much from here. The atoms are too small to see, but we get all the data that comes off here, gets sent to a computer, and then we can analyze it.
If an atom is so small, how can we know anything about it?
So quantum physics essentially describes the universe at the very small scale, or the very cold, or things that are moving very slowly.
So once you come down to that scale, what we sort of know as sort of day-to-day occurrences, sort of the way things work, doesn't really make sense or doesn't really sort of work the same way.
So we study helium atoms. So atoms are the constituent particles that form the building blocks of everything. We tend to like to think of them classically as these small little billiard balls, but in reality they're not. They have these weird quantum properties. They behave as these speared out fuzzy blobs that are much more like waves.
We try to understand reality and try to see how the world works. And when you start going at sort of these smaller scales, you start asking them more fundamental questions.
Now, the solar system is held together by gravitation.
So gravity describes things on large scale, quantum describes things on small scale. We're not quite sure how you get from small to large scales because they describe things in a very different way. So when quantum theory was first developed, because it came up with these weird predictions, a lot of physicists didn't like these ideas, and one of those physicists included Einstein. Einstein really spent his life working on quantum theory and also relativity, which is the study of gravity, and yet he still couldn't come up with a theory that coherently described both of them, which is called the theory of everything. There are a lot of physicists that are devoting a lot of time on trying to get these two theories to work together and talk to each other, and there are some theories in development. The trick is coming up with experimental tests.
Even though sort of the theory has been established and there have been many tests that have been done to show that the theory is valid, there hasn't been a test to show that the theory is valid when you look into the sort of momentum of atoms.
So this is the start of our experimental sequence here, where we have a cryogenically cooled, so that's using liquid nitrogen to make things extremely cold. We go through a Zeeman slower, which is this copper coil here that slows the atoms down from about 1,000 meters a second to less than 100 meters a second.
So then we have this beam called the push beam that pushes the atoms towards the second chamber.
This is our final science chamber, where we start with our cloud of ultra cold atoms. We then collide them and generate the entanglement. I started my PhD nearly 20 years ago, working in the same lab that we did the test today. And back then, when we were building parts of the apparatus, it was kind of a long-term goal that we could look at some of these fundamentals of entanglement. It was one of the long-term goals of this apparatus, and it took us nearly 20 years to actually be able to realize it.
That sort of has led us to this point where we can actually run experiments that test these theories, not just in sort of these hidden properties that lie in the atoms, but actually looking at their motion and stuff.
I often joke that our experiment, it's basically like a several $1 million Meccano set that you can sort of put together and play with, and yeah, we're quite privileged to be able to work on. Einstein and a couple of co-authors, Podolsky and Rosen, came up with a paper, the famous spooky action at a distance paper, where they said that two entangled particles, if you measure one, it will instantly affect the properties of another. And now they didn't like that, and they said that this just shows how ridiculous quantum mechanics is, and this can't be the way the universe works. And then another theorist, about 30 years later, John Bell, came up with a way to test that mathematically.
In the 1960s, Bell came out with a theorem to sort of test this property, quantum entanglement. And for many years, it was sort of speculated it would be hard to sort of experimentally show this. The recent Nobel Prizes by Alain Aspect, Zellinger, and Clauser, they showed that these sort of experiments can be conducted in the lab.
So most of the Bell tests so far have been done with photons, so with light. A photon is just a small particle of light. But what we wanted to do is we wanted to extend that into atoms. So atoms are different in that they're particles that have mass, so they're heavy. There's been very few Bell tests on mass, and in particular there's been no tests where the particles are entangled in momentum, so that's where they move along different paths. And the reason why this is interesting is because you could then extend that to test theories such as gravity. Because the particles have mass, they're also influenced by gravity, and so you could potentially look at entanglement in a gravitational context. What our experiment looks like is, if you take two of these billiard balls and you collide them off each other, they can either go one way or they can go the other way. Now, quantum mechanically, atoms aren't billiard balls. They're these little funny fuzzy blobs that behave in a very weird way like waves. And so what they do instead is, rather than going this way or that way, they go this way and that way at the same time. They go this way and that way. And it's only when you make a measurement afterwards that you see an atom here and say, all right, well, now they're here, or you see an atom here. Until you actually make that measurement or do something else to manipulate them, those atoms have gone both directions.
You can think about the driving force in your experiment being the laser beams. If you want to redirect the atom, which are the sort of cue balls in your experiment, to move in a certain direction, to have a certain velocity, you would change that cue stick and the force you would apply in hitting the ball. Being able to create this momentum entangled state requires that we sort of have very good control and understanding of how that laser beam works.
Our experiments are kind of at the opposite end of the spectrum to the Large Hadron Collider. They work on making things extremely fast and extremely high energy, so you can see some really interesting high energy physics. We do the opposite. We work on making things extremely slow and extremely cold, so that when I say collide and we push the atoms so they collide, they only collide at an extremely slow rate. They're moving at centimeters per second. If you could see them, you'd see them moving extremely slowly. Each experimental cycle takes about 30 seconds, and so we can run several thousand experimental cycles per day if we're running continuously. The data for this result, because we're relying on extremely small coincidences, so we have an extremely low collision rate, it's several weeks worth of continuous data, and that doesn't include all the months of setup time.
It took about a month for us to sort of see this slowly growing signal. And that was been quite exciting, because as the signal was growing, we were sort of anticipating that, oh, we're going to see these results. It was a lot of sort of wary looks. Like we didn't want to sort of count our chicks before they hatch.
It's a pretty important discovery.
I would say it's a big result in the sense that even though sort of the theory has been established and there have been many tests that have been done to show that the theory is valid, there hasn't been a test to show that the theory is valid when you look into the sort of momentum of atoms.
Theoretically, there's nothing super surprising about what we've measured. This is how theoretically we understand the universe to work. But it's one of those things that you need to measure. If we can't measure it, maybe the universe doesn't work the way we think it does. So this result confirms the predictions of over a century ago that matter can be in two locations at once, and it can then interfere with itself even in those locations. Now, in terms of what that actually means, that's still an open area of research. I'm just an experimentalist. I tend to just follow what's called the shut up and calculate approach, which basically says that we know how to describe this with maths in a way that we can predict exactly how our experiments work. Yes, there might be some weirdness, but that's kind of above my pay grade. So one of the big questions is, where does quantum mechanics stop and where does classical physics start? At what point do you stop seeing entanglement? And so that's one of the reasons why it was really key for us to show it with atoms. Many of the technological breakthroughs of the last century have come from understanding the fundamentals of quantum mechanics. And many of the predicted big breakthroughs of the next few decades are also going to come from fundamental quantum mechanics. Now, we don't necessarily know what all those breakthroughs are going to be, but it's through looking at this basic research, through understanding the basics of quantum mechanics, that's where all the best physics inventions have come from.